right. Hey, everybody. Today we're going to do topic 19. And before this recording, what I was going to say is that I do recommend you start working on your project. You don't have to get into all of the regression modeling yet, but I think getting some of the EDA and the data exploration out of the way is a good call. Like, for example, yesterday we talked about some EDA that you could do that is going to be useful for this project, like checking that all of your features are linearly related to your target. Also, on top of that, if you decide not to go with the data set that is provided, let me know. I would like to see what data you are working on first, just so I can make sure that you're not going to go down any rabbit holes of like, this is not the right kind of data you should be using. So please send over your data set if you're not using the provided one, although no pressure to source your own data at all. Okay, so today we're going to expand from our linear regression from yesterday, which was only 2 variables, 1 target, 1 predictor. And today we're going to use multiple predictors to predict 1 target. So to start, we're going to import some libraries. And today we're only going to introduce 1 new library at the very end, sklearn, scikit-learn. Actually, scikit-learn is a library that we're going to be using a lot of, especially phase 3, 4, and likely in your capstone as well. And so we're going to start talking about it today. I'll outline how you will be using this in your projects because pretty much scikit-learn and stats models do very similar things. Next week, I'm going to go over an entire project outline and how that'll look. And I think that will help to illuminate like how we're going to use all these libraries in tandem. So scikit-learn is the new library that we're going to talk about. It's a very like machine learning. It is the machine learning library. But everything else you've seen before. Okay. So the first thing we're going to do is yesterday we talked about our simple linear regression with 1 variable. And at the very start, I said that in statistical learning theory, we build models for 2 things. 1, to learn patterns about our data. 2, to make predictions on future data. So with stats models, I didn't really talk about how we can make predictions. So let's talk about that. So remember, this was our data that we had yesterday, our weight versus height. We had the formula. This is how we ran our regression. We had our R-squared of 0.955, and then our coefficient, the relationship that we deemed that we discovered through this model was that 1 increase of height of 1 unit will increase weight by 5.539. So that's a relationship that we learned from our model. So that's one of the things that statistical learning theory does for us. The other thing that we do is prediction. So how do we make predictions? So actually, this is just random code. All right, so the way that stats models makes predictions is a little bit more finicky than with scikit-learn. So actually, I'm going to go over this process again at the very, very end with scikit-learn with a different data set. But the way that you can use stats models.predict is you actually use the .predict function that comes from the model. So model is what we fit over here. And you can basically do model.predict. Now, why I say it's finicky is because stats models, for some reason, will only take in data frame rows that match the data frame of your input values. So this was our input data frame, our df.head, and it only works on data frame rows. So like this. So I have a height of 71, weight of 192. And if I do this, my .predict, I end up with 188 as our prediction. So 188 was our y hat, if you remember our y hat, and 192 was our actual y. And so in this particular person, there's roughly a 3 to 4 pound error. So that's how you use .predict within stats models. In something else that you can do is write like a simple piece of code. And this one, just because I'm being lazy, I just feed it in an index number from the data frame. Since I know there's 20 data points here, any number between 0 and 19, fair game. So for example, point number 19, actual weight 171, predicted weight 177. If I look at point number 1, actual weight 201, predicted weight 188. Point number 5, you get these numbers, so on and so forth. Alternatively, you can use the coefficient values to create a function to predict any height, because likely that's what we want to do, right? We want to predict for points that are not already in our data set. So what we can do here is by using the coefficients and our knowledge of like the straight line formula. Sorry, let me zoom in a little bit for y'all. Our knowledge of the straight line formula where it's intercept y equals to mx plus b. So we have y, which is our weight, equals to mx, and then plus b, our intercept. And just by applying that formula and the coefficients that we got from our model, I basically copied those numbers over from here. We can create this function to, given any height, give you a weight. So here I have this predict weight function that uses this and returns the weight values for any height in inches. So here with a height of 55.8 inches, predicted weight of this number of pounds, I can pretty much plug in any number, even things that are not possible, and you can get values there. Any questions about making these predictions? So pretty much you can put in any height value and it'll give you a weight prediction. All right, let's move into multiple regression now. A lot of the concepts that we talked about yesterday do also apply to multiple regression. So for example, the linearity assumption, you have to check that each of your features are linearly related to your target. Also the normality assumption, as well as the heteroscedasticity or homoscedasticity assumption, those both you can check for your model as a whole. And we'll go through what those look like next week as well. And also in some of your labs, they have the code to do that for multiple regression, but it's pretty much the same thing. So for this multiple regression, let's look at our trusty miles per gallon data set that we talked about, that we used, I think, a few times last phase. So how we set up our multiple regression to start is formula, same thing, just instead of one feature, you just put a plus sign in between everything else. Now these names, they draw from your column names, so they have to match your column names. That's something that's good to remember. Also, notice that the ones that I'm using, these are all numerical values. I'm not using car name for this task because linear regression does not take in string values. I'll show you all an example of what you can do with string values later on. But once you have this formula set up, the rest of the code is actually exactly the same again. Feed in your formula and data into OLS, call .fit at the end of it, and we have our summary. So the way that you interpret this output is very similar to the output that we had to interpret yesterday. So R squared of 0.82 is just saying that 82% of the variation in miles per gallon can be explained by all 6 of these features. Coefficients can be interpreted the same way as well. So let's go with acceleration to start. So acceleration has a coefficient of 0.155. So basically an increase in 1 unit of acceleration will increase our miles per gallon by 0.155. Same thing for year, increase of 1 year will increase our miles per gallon by 0.76. If it's negative, an increase in 1 cylinder will lower your miles per gallon by 0.447. So coefficient you interpret the same way. P-value is also the same. So remember how yesterday we actually didn't have any instances of insignificant variables, but here you can see that we have anything below 0.05. So technically it's just this one, just cylinders. And cylinders has a p-value of 0.167. So that just means that there is a 16.7% chance that the relationship that this model found between cylinders and miles per gallon is completely random or is just statistically insignificant. So what we do with these, usually if you have anything that is insignificant, we either want to remove it or change it such that it could be significant. And we'll talk about some of the ways that we can make things more significant in a little bit. But again, out of this output, the main things that you want to look at are squared values, coefficients, and then p-values. Any questions at this point? All right, so the next thing I'm going to talk about is categorical variables. So I'm just going to print a bunch of histograms for each one of our features. So here we have every feature against miles per gallon. So miles per gallon is always on the y-axis, and then each of our features is down here. I split it up into 2 groups, things that I think might be continuous and things that might be categorical. So what is continuous? Continuous is basically like if you can have values between the discrete values. So for example, displacement values can range from, I guess, around 100 to 400. And I think the displacement values are, they could technically be floats. You could technically have a 0.5 value and that's fine. Same for horsepower, weight, and acceleration. The values can be all over the place. Now, I think a very easy way to check if something could be categorical is also do a scatter plot. And if you see this kind of pattern, like this kind of like a lot of lines pattern, that's just saying that, you know, the values can only be certain values. I mean, yeah, the numbers can only be of certain values. So for example, the cylinders can only be 3, 4, 5, 6. I assume 7, I don't know. Anyway, it's 3, 4, 5, 6, and 8. And the origin can only be 1, 2, 3. I don't know much about cars, but I imagine you cannot have half a cylinder. I also imagine you cannot have like half an origin. You're debatable. And when you're thinking about should these be considered categorical variables or not, there are several things to keep in mind. So first, and I'm going to annotate a little bit here. First, look for kind of the linearity assumption as well. So here you can see that with cylinders, I sort of see that it goes around like up, it goes a little bit up, and then goes back down. So because of this actually doesn't really fulfill the linearity assumption. So therefore, cylinders would be a good one to consider categorical. Year, I would argue, looks like could be linear because roughly it is in a line. And origin, hard to say. I would say that if you're unsure, it is not uncommon to just run a model once with it as categorical, once with it as continuous, just to see if anything is significant, insignificant, if it affects how your model performs. So yeah, so what we're going to do in this example, we're going to just assume that cylinders, year, and origin, let's just turn them all into categorical variables and see how it does. So the code that you use for turning something into a categorical variable or treating a variable as categorical, and you can also definitely do the same thing if you have like names. I just know I have a lot of unique names here, so I don't want to do that. But let's say I had like car brand and I had like just maybe like less than, I don't know, like let's say I only had 10 different car brands represented in this data set, I could consider doing the same thing. So what you do here is you use the pandas.getDummies function. And so getDummies creates dummy variables. And let me actually just run this first to show you all what that looks like. All right, so I created dummy variables and I concatenated them all together with the original data. So what I have here is, let's say for cylinder, what I did was for every unique cylinder value, it creates a column of zeros and ones. And for the zeros and ones, it's just to denote whether that that cylinder value is fulfilled or not by that row. Something else to note is I did drop first equal to true. So remember how we had 3, 4, 5, 6, and 8, and here we only see 4, 5, 6, and 8. This actually is related to the multi-collinearity problem that I'm actually going to talk about next after this section. But we always drop first equals to true. In brief, it's to prevent redundancy. So pd.getDummies, and if we want to look at just one of them, it just looks like this. At any one row, you can have at most 1, 1, and the rest has to be zeros because these are categorical dummies. And the same thing was done for the years. You can see that we have a value from like 71 all the way to 82. And for origin, I think it was just 1, 2, 3. So now we just have the 2 and 3. If it's all zeros, that means that the origin was 1. All right, so let's just throw this into our model again. So I have my data here, and these are going to be all of the columns that I'm going to be running through as my features. And instead of just typing them all out manually, what I'm going to do is run this, where I'm doing the plus.join so that this is automatically created for me, so I don't have to type out everything manually. And let's just see how this fits. All right, cool. We have an output with a lot more features than we had before. The R squared, I think, went up. Let's check. 0.874 compared to before we had 0.821. So R squared went up. So it's explaining more of our variation in miles per gallon a little bit better. But let's take a look and see what our p-values look like. So our p-values, there are a bunch of insignificant ones. acceleration has a 0.96 p-value, which goes to say that this relationship of 0.0036 that this model detected pretty much occurs by random. It's not significant at all. A bunch of other insignificant p-values, which tends to happen when you have so many features. And I'll talk about why that is in the next section as well. But you can see here a bunch of p-values that are above 0.05. So we got to do something about that. With these coefficients, how do we interpret coefficients in the case of dummy variables? It kind of is in a similar way as you would for a continuous variable, but the drop first has something to do with it. So if you remember before, we had cylinder 3, and cylinder 3 isn't represented as one of the columns here, but cylinder 3 is still represented in the model. So now this coefficient of 6.9399, this would be the difference of having 4 cylinders instead of 3. So that's how you interpret these coefficients for dummy variables. Instead of 3 coefficients, instead of 3 cylinders, having 1 additional cylinder, 4 cylinders will bring your miles per gallon up to 6.94. Same for the rest. If you have 8 cylinders versus 3 cylinders again, your miles per gallon will go up by 6.3668. Same for years. And for years, you can see that there's some high p-values going on over here, but you kind of evaluate both of those columns slightly differently and independently as well. So for example, the original year that we had to drop was, because of the drop first, was 70. So having a car made in 71 versus 70 increases your miles per gallon by 0.91. These will decrease being in 72. And then, yeah, from this, it's actually pretty neat. You can sort of see a pattern that, like, between the different years, where is miles per gallon higher? So just based on all of these coefficients here, from 71 to 82, we can see that the year 80 is probably the highest miles per gallon, even compared to 81 and 82, because these coefficients are all relative to each other as well. So I know I said a lot about interpreting this, and it does take a bit of practice and thinking, especially in context, but any questions at this point? All right, so next what we're going to do is we're going to deal with these high p-values. This process of getting rid of high p, or I should say first, whatever your final model is in your project, or whenever you're asked to do a linear regression model, you should not have any p-values above 0.05. Having p-values above 0.05 is sort of like, why do you even keep that there? Because that relationship is not significant at all. That coefficient is probably not accurate, so therefore you don't want to have that there. So just know that for your projects, for whatever your final model is, you don't want to have any p-values above 0.05. Now, there are different things that you can do if you have a high p-value. Like, for example, later we're going to talk about transformations. You can also feature engineer brand new features out of insignificant features. Next week, we're going to talk about other things that you can do as well. But one thing you can do just really quickly off the bat is just drop high p-values, or drop columns with high p-values. So here, let's see, let's drop acceleration, and let's drop any year before 75, or actually before 76. So here we've dropped, I just copied and pasted the same formula. This doesn't have acceleration anymore. I think I might have also gotten rid of displacement because it's above 0.05, and got rid of the years before 77, because those are all insignificant as well. And let's see how that affects our model. All right, so now that we've taken away all those high p-values, none of our p-values are insignificant anymore. That's good. Also, you can see that our R-squared actually wasn't affected too much. It went from 0.874 to 0.869. And we took away at least 5 variables, and our R-squared only went down by a very little bit. So that means that those variables did not contribute very much to begin with. So it's a good decision that we took those out. Now, as a side note, sometimes you want to get rid of p-values iteratively. When you get rid of p-values, and when you get rid of columns with high p-values, your coefficients will change. Your other p-values will also change. So for example, let's see, cylinder 6, which I didn't drop, had a p-value of 0.012, Now cylinder 6 is back down to 0. So by removing features, your model just fits in a different way. So it's not uncommon to, after you drop your first set of p-values, if you happen to have a lot of variables, that maybe something else happens to be insignificant again. So just know it is going to be an iterative process, and this is very much what your project is going to look like. Okay, so the next thing we're going to talk about is multi-collinearity of features. Note that I say of features, that's something that's very important to remember. So what does multi-collinearity mean? Multi-collinearity is whenever any of your features are correlated with each other. To contrast, there is that linearity assumption that assumes that says that you have to have your features correlated with your target, but features by themselves should not be correlated with each other. And the whole thought behind that is, if let's just say that I think weight and horsepower are highly correlated with each other, and they're both also highly correlated with miles per gallon. If you can use weight to predict miles per gallon already, since weight and, did I say displacement or horsepower? Since weight and displacement are already correlated with each other, it's going to show you very, very similar impacts to miles per gallon. So that's just saying that since both of them are correlated with each other, there's going to be some redundancy there. So let's go through a process of looking at multicollinearity. So to simplify, let's just do a very, very quick linearity assumption check. So here I'm doing data.core. So core is a pandas function that will just take every column, every numerical column, and give you the correlation coefficient between each of them. So what I'm going to do here is, we can see straight off the bat, high correlation between horsepower and displacement, weight and displacement. Even on the negative side, 4 cylinders is highly correlated with displacement. There is no set threshold that you have to say, like, okay, as long as it's above this number, I have to drop it. It's something that you kind of tune and test on your own. So again, very, very iterative process. So to start, let's just check for linearity. From this correlation table, I can pull out just the miles per gallon. And I would say that for your project, don't do this, because this is just to simplify this process right now. But I'm going to set a threshold and say I'm only going to keep any column that is more than 0.3 correlation, that has more than 0.3 correlation with my target. And this is for linearity. So for linearity, I've only kept these columns. I've only kept displacement, horsepower, weight, acceleration, cylinders 4, 8, these 2 years, and that origin. Just because those are the only ones that are have a correlation of higher than 0.3 with miles per gallon. All right, so set 1, these are the features that I'm going to use for now. Usually in a project, you wouldn't just cut off so many features all at once. This is just for simplicity's sake. Okay, so let's just run the model with features that are correlated with miles per gallon. All right, so you can see here 0.81 r², which I think is not too bad. However, we have a couple highly insignificant variables. Like we have acceleration as a 54% chance of being random, displacement 0.28, also not good. So typically when you see high p-values, it's insignificant and it could be a sign of multicollinearity, which we know that it is because we saw earlier that displacement, weight, and acceleration are all correlated with each other. If we remember, see displacement and weight and displacement and horsepower, all highly, and acceleration as well, all highly correlated with each other. So there is some redundancy there. So what we can do, and this is just look at the correlation table again, this is a whole chunk of code that I took from one of the labs, which I think does this in a really neat way. It looks for pairs. It just reorganizes this. I think does like a stack and reorganizes this into a way that's easier to take a look at correlations. So what this is doing is basically looking at, okay, miles per gallon with miles per gallon, this is the correlation. It takes every pair and gives you that correlation number. Through this code, it basically works through this with pandas functions and turns it into something like this. Of course, we drop anything that is a perfect one, because if it's perfect one, it's likely it with itself. And we look at what else is highly correlated. So based on this, it looks like weight and displacement, and horsepower and displacement, weight and horsepower. These three are highly correlated with each other. There's also cylinder 8. There's also, I think, a bunch of these correlations here. So let's drop some variables that are highly correlated with other variables. We have this 3-way correlation here. And if you have 3 things that are correlated with each other, you actually want to drop 2 of them so that you only need your data represented by one of these columns. Now, which one to keep is very much up to you. It sometimes depends on context. Like, for example, okay, if I want to keep a variable, I want it to be the one that I can most easily obtain values for. So for example, if I'm deciding between keeping weight, displacement, and horsepower, maybe I want to think more in a business case. What is the easiest thing for me to get? Probably the weight of the car. I don't know. Is it easy to find the horsepower and displacement of a car? No idea. But let's just say I think that weight is the easiest data to gather, so I'm going to keep weight. So here, let me just try this example here. And this is just refitting things that are not correlated with each other. This formula is here, and we'll run this over here. No insignificant p-values. Something else that you can do, also just see between weight, horsepower, and displacement, which one gives you better results. That's also something that you can do. So which one gives you the highest R squared? So this is 0.794. Let's say I want to test it with horsepower. And then I fit that there. 0.782. I already forget the number from before, but you can basically try different combinations and figure out which one. What's the other one? Displacement? 782, 754. Figure out which one gives you the best result out of the 3. And it is a fairly involved process. So as long as if you have a reason for picking a variable over another variable, put it in your markdown and you'll be good. So multicollinearity is actually another assumption of linear regression. And it's specifically for multiple regression, just because if you only have one feature, there's nothing for it to be multicollinear with. So that's something that you have to check for as well. And it's probably going to be one of the iterations of your modeling process. All right. Any questions at this point?
Yeah, I have 2 questions. When you say the best result out of 3, what are you looking for as the best result?
That's a good question. 2 main things that you would look for. I would look at the R squared. So I was actually looking at the R squared earlier and seeing how it changes when I use a different feature. So R squared is one of them. The other one, I would look at the root mean squared error. And root mean squared error, I haven't talked about yet, but I'm going to talk about the end of this notebook.
So the higher the R squared, that's the higher the root mean square, that's the one that you want to keep.
Higher R squared, but lower root mean squared error. I'll talk about root mean squared error later in a little bit.
All right. And just to go back a little bit, how were you able to get those 3 columns, how were you able to pinpoint that they were correlated?
Oh, yeah. So with this output here, this code is fairly complicated and is one of the harder pandas things to do. So I just took this from the lab. But basically, I looked at it over here. And then these all have high correlation values. And really just by looking, I saw that these 3 were correlated with each other. And then what this code is doing is basically taking this here, this correlation matrix from here, and just shifting it into first this format. That's what they're doing with I think that's what they're doing. No, actually, that's what they're doing here. All of this turns it into this format, and then the rest of this code turns it into this.
Okay.
Yeah. I would say it also took me a little bit to look at every single method that they're doing. I actually took this apart, did it one by one. I was like, okay, that's what's happening there. Okay, now I add dot absolute value. That's what that is. Dot stack. Okay. I right now cannot tell you what that's doing either.
All right. Thank you.
You're welcome. Anything else? All right. Okay, so let's take a look at transforming features. So transforming features is something that you can use to get around the linearity assumption as well as multi-collinearity assumption. And also depends on what kind of transformations you're doing. So I would group transformations into two groups: transformations that change the distribution of your data and transformations that do not. So first, I'm going to talk about transformations that change the distribution of your data, and that's, for our purposes, just log transformations. So let's just take a look at some of these continuous variables. We had these scatter plots from before. These are our four continuous variables, and you can see that they're, like, I guess, kind of linear, but not as linear as I would like them to be, maybe. So this is still more of a curve where I feel like it could be a straighter line. And that's what we've got for pretty much all three of these. And this one, you can argue, I don't know, looks not as linear as it could be. So we can make this more linear by doing a log transformation. So log transformation, all we have to do is do numpy.log on all of that data, and it does a log transformation for you. And let's just see how that changes. It's actually pretty interesting. I don't want to do a dot histogram. I want to do a scatter plot. Let me do this, pull that over here, and let's do a data log. Okay. Hope this is right. Oops, hold on, give me a second. Not acceleration, and then we want log displacement, log horsepower, and sorry, bear with me for a little bit. I edited a lot of this code during the study group earlier. Log horse and then log weight. Okay. And then miles per gallon. Let's do data miles per gallon. Or I think it's, yeah. Go. Never mind. I'll just show you all the scatter plots separately. Plot.scatter of data log dot, and then car df mpg. Okay, there we go. Okay, so we don't need that. Okay, so this is displacement, which at first looked like this, but after the transformation now looks slightly straighter. So this log transformation has changed the distribution of our data. It actually takes the extreme values that are low and high and kind of like flattens them out. So if you usually if you see some sort of skew like this or anything that's nonlinear, log transformation tends to help. And we can do the same thing for we can take a look at the same thing for the other columns as well. So this is displacement. If we want to look at it for horsepower, you can see that horsepower went from looking like this to this. And then finally, log weight, also a much straighter line. So you can get a stronger linearity assumption by doing a log transform. There are some downsides to doing this, and I'll talk about those downsides in a little bit. Basically, it comes to what do you do about the coefficients? So now, instead of putting displacement in here, we would use log displacement. And so the way that you would interpret that coefficient is that 1 unit change in log displacement causes miles per gallon to go down by 0.361. And that's kind of the con of using a transformation, is that you have to do that reverse transformation later. So one way that you have to do it, you kind of have to reverse transform it. You basically have to reverse transform the coefficient. And I like to think about it mathematically. So let's just say that log of displacement, and I'm just going to call it log D. When I increase log displacement by 1, my miles per gallon increases by, actually, in this case, it decreases. Let me just undo that. Decreases by 0.0361. Let's just say 0.03 of mpg. All right, so this is a change in the log of displacement. If I want to look at a 1+1 change in the displacement, this changes miles per gallon by exponent 0.03. There's just one additional step that you have to do if you decide to do a log transform. And then you will just have to evaluate whatever this number is to figure out what the actual effect is. Questions about interpreting these coefficients? I would say it makes more sense like when you've already like finalized the model and then you realize, okay, I had logged it here. How do I interpret? Okay, awesome. So interpreting coefficients just becomes a little bit harder when you log transform, but sometimes it's worth it because it helps your linearity and it helps make your model stronger usually. Okay, so this log transform is something that does change the distribution of your data. So if you actually look at the histograms from from before we did the log transform, let me see if I can do histograms. Hist, is it kinda hist? There we go. All right, so you can see that the histogram is slightly different. This looks to be incorrect. Anyways, y equals to, never mind, we're gonna ignore that for now. But basically the distribution of your variables do change. Okay. So log transformation changes the distribution of your data. There are these other transformations that do not change the distribution of your data. And there are reasons for using them, which I'll talk about in a little bit. But these are some of the more common ones. I would say these two are the most common: min-max scaling as well as standardization. So min-max scaling basically will take all of your data and smush it such that it is between the values of 0 and 1. Important to note, it smushes your values between 0 and 1. So you cannot have any values below 0, above 1 after you go through this transformation. The next most common transformation that you do is standardization, which is basically our z-score from before. So find the mean of your data. You'll just take the value minus the mean divided by your standard deviation. So same as your z-score, it just turns everything into like something that's centered at 0 with a standard deviation of 1. Now, these two transformations are the most common. There's still mean normalization and unit vector transformation. I would say that these are more similar to doing min-max scaling, but min-max scaling is still the most common one. There's a big difference between these two, is that min-max scaling is bounded and standardization is not bounded. By bounded, I mean that the values for min-max scaled data has to be between 0 and 1. And for standardization, there is no upper and lower limit to your values. If you have a number that's just like very, very far away from your mean, you're going to get a much bigger number relatively. And so it is important to think about which kind of scalar you want to use for your data. And how you think about that is, let's just say that we have, and the situation in which you want to think about that is when you have things like outliers. So let's just say we have a distribution with outliers, and I'm just going to draw a couple axes to show. So let's just say I have a distribution of data that looks fairly normal like this, and at the end I have an outlier like that. In min-max scaling, because your values are coerced to be between 0 and 1, you're going to have data that looks like this. Everything is between 0 and 1. And then most of your values are going to be within this range of like, I don't know, 0.3 or something like that, for example. However, if you're using standardization, your values are unbounded. So therefore, your data will be more like that. And so your values are not constrained. They're really still in terms of how many standard deviations away from the mean. So something to consider. I will tell you that because the shape of the distribution doesn't change, it's just kind of shifted along the graph and also just stretched or compressed. Because of that, when you transform variables in any of these methods, your p-values will not change. Your r-squared will not change. The only thing that will change is your coefficients because they're just on different scales. Questions about that? All right, so why would you then want to transform your data? One use case for transformation is, let's just take a look at our coefficients over here. Let's just use this as an example. So let's just say in doing this analysis, we want to figure out, okay, what feature has the strongest impact on our miles per gallon. Strongest impact, you can sort of interpret that as the highest coefficient. And so you would say, okay, the highest coefficient here is the year being 80. The year being 80 would be the strongest contribution to miles per gallon. That's one way that you can interpret that. However, that's kind of not fair, right? Because the way that we interpret coefficients is like a 1 unit change in your feature. How does it affect miles per gallon? So of course, 80 that can only take a value of 0 or 1. Of course, it'll have a much higher coefficient versus something like displacement. And displacement, as we saw from our data before, let's just print our data real quick here. As we saw from our data, displacement is measured in like the hundreds, the range of hundreds. And so of course, a 1 unit change in displacement is not going to affect miles per gallon very much. And so the purpose of scaling our data so that our values are between 0 and 1 is so that we can do a little bit more of an apples to apples comparison between our variables. And at the very end, I think we'll see an example of that. Any questions about transformation of features? All right, I will say that part of the process is, let's say you run some models without any transformations. You think, okay, maybe based on my EDA, I think I might want to try transforming these variables, do a transformation, run a model and see how it goes. All right, so these are all transformations. And then the last thing I want to talk about is model validation. But before I get into that, because that's kind of like a different library, any questions about this stuff? Actually, why don't I run something with transform variables? I think I have transform variables here. This is going through all of the transform variables. And let me just quickly grab some code from the top so we can see how that is done. All right, so we have this here. We have data being data bin. We need our formula, which is, let me just grab the formula real quick. Okay. Yeah, any questions while I do this real quick? Okay, and data bin.column. Okay, cool. So with all of this scaled data, okay, this is kind of hard to interpret, but basically our R-squared is perfect, which is kind of suspicious. But anyways, we have high p-values here. But now you can see that our coefficients, they're all very small, but they're all around the same scale. I should have taken out miles per gallon from there. Actually, hold on, let me just check something really quick. Miles per gallon. Let me just do this. Okay, there we go. This makes more sense because we have miles per gallon in there. Anyway, so now we have this R-squared. We have some insignificant variables, but now because we have scaled all of our data, let me just double check that this is scaled. Now that we have scaled all of our data, our coefficients are all more on the same scale. Even though we had acceleration, displacement, horsepower, and weight values that are very different from 0 and 1 at the start, because we scaled them to become 0 and 1, now we can figure out what actually has the strongest impact is when we do more of an apples to apples comparison. So based on this, we see that something that's one of the higher numbers is horsepower, high number in the negative direction. And horsepower was one of the ones that always had very small coefficients. And so because we scaled it, we can actually see that a 1 unit change in scaled horsepower will lead to a -11 miles per gallon. So it's actually pretty hard to reverse transform something like this. However, what some people do is they'll actually take a scaled version and an unscaled version for 2 different purposes of modeling. One, to learn about the impact of your different features to your target, and then once to just have like, the straight up coefficient interpretation. Any thoughts or questions about that? I recognize that we've talked about a lot of new things today. So does anyone have anything they want to clear up? All right. So last thing I want to talk about is model validation. And I had this over here. So model validation and the need for what's called a train test split. So far, we've just been fitting our models to data, and we're just evaluating using data points. So for example, in our weight and height example, we could make predictions and also evaluate our overall error just by looking at, 125 and 116. Okay, we're about maybe about 9 pounds off. If I do this, oops, is there no, oh, anyways, I think I overwrote the, but anyways, so far that's all we've been able to do. However, the purpose of doing predictive modeling is to very likely use your models to predict on other data that your model didn't have to start with. And so how we do that is through a process of train test split. And the thought behind train test split is whatever data set you have, you take 20% of the data. Of course, this number can change, but for the most part, it is 20%. You take 20% of your data and you don't show that to your model. Then you train your model on, or you fit your model on 80% of your data, the other 80% of your data, and then test how well your model is doing by using the values from the 20%, getting predictions and comparing how close those are. We're going to go through that process right now. And in looking at this train test split, you can figure out if your model is underfitted, fairly good fit, or overfitted. And I'll talk about when you would detect those things. So for checking for fit, you would look at root mean squared error. So that's the metric that I talked about earlier. Root mean squared error is basically your y minus your y hat, just the error of your predictions. So we're going to use this regression again. We're going to use this data set again. And we're going to use a different library to run a regression. And you'll see some pros and cons because we're going to be using the scikit-learn. We're going to be using the scikit-learn version of linear regression. So first, let's get all of our data. Now for scikit-learn, you have to separate your y and your x. So here our x is just, so far we're just going to use these to start. And then our y is just our target variable. That's our x and y. And I mentioned train test split. This is how you use your train test split. It comes from scikit-learn as well. Scikit-learn pretty much has almost the whole machine learning process in there for you. So next phase in phase 4 and for capsuling, you're most likely going to be using scikit-learn a lot. But we're going to use train test split to automatically shuffle and split our data into random subsets of 80 and 20%. So after this is done, we can take a look at our X train. Actually, let's look at X test since this is here. X test looks like this. You can see that the index numbers are shuffled and it only has 79 rows as opposed to, I think, 300 over. X train, also the 4 columns, but 313. So this is our 80%. And then we have our X test, which is our 4 columns, 79 rows, and then our Y train and our Y test looks like this as well. So Y test is what we're going to be comparing our values against. So we're going to talk about this syntax a little bit more later on, but how you use linear regression from the scikit-learn library is slightly different. So what you have to do is import it first. What this step is an instantiation. You're basically giving it an empty model. And then this dot fit will fit your empty model to the data. So that's why I'm giving it my X train and Y train. After that is fit, and I call it linreg for linear regression. After that is fit, I can make predictions on the train or the test set. And so let's take a look at what this yields. So let's look at Y hat train. Y hat train is basically an array of numbers. And these are your Y hats. These are basically predictions. And then you also have your Y hat tests. These are also predictions, matching the number of rows in your test set. How this dot predict works, if you remember, our X train had these 4 values: acceleration, weight, origin 2, origin 3. And this acceleration is also scaled. So dot predict works in a pretty neat way. Linreg dot predict. You can do a numpy dot array and just feed it in. And just feed it in any 4 numbers that match this format. So let's just say I want to see what would the miles per gallon be for a car that has an acceleration of 0.7, a weight of scaled weight, by the way, a scaled weight of 0.9, origin 2 is 0, origin 3 is 0. When I run that, it gives me a prediction of miles per gallon of 19.10. So that's what's happening over here, but for your test sets. So now that we have these predictions from our X-train and X test, we can see how much error there is on average by comparing it to the actual values. So a good bit is going on here. First, scikit-learn also has a bunch of metrics that you can just import and use. So let's take a look at this. We have the mean squared error between Y train and Y hat train. Remember, Y train was our actual Y values, and Y hat train was our predicted value. So we just want to see the average error between that. That's our train MSE, which happens to be 16.79. We do the same thing for our test set, error of 16.5. And then we can just take the root mean squared error because those errors are squared. Take the root mean squared error, and both of them are around 4, which is a good thing. An error of 4 is just saying that on average, our model is about 4 miles off 4 miles per gallon prediction. So it's plus minus 4. So these results are actually really, really good. The fact that these numbers are close to each other is good. Now, just remember that our model did not see any of our test data at all, yet it was able to get a pretty similar error value as the train set. Typically, if you see high error values on both sides, that's a sign of underfitting. And if you see that your train error is low and your test error is high, that's a sign of overfitting. And overfitting, you can sort of picture it to be something like this. When you overfit your data like that, if you have brand new data that this hasn't seen before, this squiggly line is just not equipped to fit to the new data. Cool. With that, I know that we talked about a lot today, but any questions? I feel like it might be like good to just sit and marinate with this new information for this week. All right, well, that's all I had to share for today. I think after today, you can sort of start working with the project, although next week, Tuesday, I'll be going over like the project guidelines. The doc is already linked on your homeroom, but I'm going to go over the project guidelines and sort of like, how do you structure your project? Because I think that's something that a lot of students are like, how am I supposed to go about this process? So I'll talk about that on Tuesday. But for now, I would say like the labs for topics 18 and 19 specifically are going to be pretty important. So I do recommend going through those. And if you're interested in looking at a full-fledged like linear regression process, in your appendix, there's actually a good, something that's pretty neat. Let me show you all. In your appendix, go to student view. At the very bottom, there is a multiple linear regression project. So if you're interested in seeing like, okay, what does this project look like if you're just like walking through the entire process, this is something that you can do. It doesn't include any of the topic 20 stuff either. So yeah, feel free to take a look at that if you feel like you just want to get into like a worked example of a project rather than going through like, I know the labs here is like one thing at a time. Sweet. Any questions to end off? All right, don't forget to get your blogs done. They have to be done preferably before the start of next week. And then, yeah, I think, oh, Monday is also off. I forgot to tell you guys. Monday is also off in lieu of 4th of July, so I will not be on Slack, but you all can still Slack each other with any questions that y'all have.
Oh. Thank you very much.
You're very welcome. Have a good rest of your evening, guys.
Good one.
Bye.
Come on, guys.
Have a great night.